This video is produced for those students enrolled in the EPO 312 Turbines course held at Cal Maritime. The discussion for this video is on gas turbine construction, and this is the first part. The primary reading for this section is out of the Naval Gas Turbine System Technician Manual that is provided electronically on Brightspace. This is a very good comprehensive read that covers all the material that you will need to understand for the completion of this section of the course. I also put in two helpful websites. One is General Electric Power Generation, and the other one is MAN Turbo Machinery. These are very comprehensive, good sites that can give you information on the latest generation of gas turbines. Primarily, we will be talking about the GE LM2500 gas turbine in this course because it is heavily used in the marine industry. It is an aeroderivative in that it was originally intended for aircraft and has been modified to use in the marine environment. The development of these gas turbines is very, very expensive, so it was easier and cheaper to take one designed for aircraft and then modify it rather than specifically designing it from scratch for maritime. Now, when you look at shoreside, gas turbine combined cycle plants have become very, very prevalent in the shoreside power generation, and that market is large enough that you are now seeing engines developed specifically for shoreside power generation use. We're going to start out the discussion talking a little bit about the Brayton cycle and how it differs from the Otto and the diesel cycle. Now, primarily, the Otto and diesel for the internal combustion engine have a set sequence of events. You have intake, compression, power, and exhaust. The difference on the Brayton is that it is all happening at certain sections of this engine continuously. So it's not where you go intake, exhaust, or combustion, exhaust, and then go back. It is happening down the length of that engine on a continuous basis. It is also, the combustion takes place at a constant pressure. Now, with the internal combustion engine, you're compressing the air in the cylinder, and near top dead center where you have the smallest clearance volume, fuel is injected or is ignited within that very small confines. So it is a very high pressure, high temperature burn, and it takes place within fractions of a second. The Brayton cycle is more like what you would think of as a boiler, where I have a continuous airflow going through the combustion can. I'm mixing and igniting the fuel and have a continuous burn. And we can control, or the designer can control the air temperature in that combustion cycle by controlling the fuel-air mixture. So it happens at a lower temperature. The advantage to that is a lot of the emissions do occur during the really high temperature, high pressure that you see in an internal combustion engine. At this lower pressure and lower temperature that the Brayton cycle occurs at, you have less pollutants such as NOx being produced. But anyway, let's look at the Brayton cycle itself. In this, you have the air inlet, so it's flowing into the compressor section of the gas turbine. It is compressed over as many as 16 stages. And as you can see as it goes through, as the pressure goes up, the volume is decreasing. It flows out of the compressor section and into a divergence into this expanding combustion can, where fuel is mixed and combusted. And then as that fuel burns and the temperatures are going to suddenly dramatically rise and the volume will increase because of that temperature rise, then it flows into a nozzle, a turbine blade, another nozzle, another turbine blade, and then it exits out the exhaust. So these turbine blades are extracting power which goes along a shaft to power the compressor section of this gas turbine. So this blading is there to generate the power needed to compress the air for combustion. Now, when you look at these two graphs down below, you'll see the first one, we have volume increasing up to the right along the bottom and pressure increasing as you move upwards. So from the air inlet to the compressor outlet, what we see is an increase in pressure and a decrease in volume. And then as it goes into the combustion chamber, we see a volume increase because of these burning gases, but it's being held at a constant pressure. Then as it goes through the expansion part of the turbine, then what we're seeing is the fact that it is expanding and going down to atmospheric and it's exhausted. On the second one, we're looking at pressure being vertical and temperature increasing as you move to the right. Now, with this, again, we're seeing the pressure going up as we go through each stage of the compressor, but we're also seeing a temperature increase, and that temperature increase is because of the heat of compression. Again, combustion is taking place at a constant pressure, but we see a dramatic increase in the temperature of the gases. Then they expand through the turbine blades where you are extracting energy to run the compressor, and then again exhausted. So this is a continuous cycle where you have compression, combustion, expansion, and exhaust happening continuously and each sequenced by where it is on the axis of this engine. Okay, so again, intake, compression, combustion, expansion, and exhaust. One of the large effects, and this is a disadvantage of the gas turbine, is it is as much as 10 to 20% of its efficiency can be affected by outside air temperatures. If you're talking about this turbine is running in San Francisco with a 55-degree air temperature at atmospheric sea level, the air will be very, very dense, and that affects the mass flow rate going through the engine. This very dense air is going into a constant area, right? The intake of this engine is constant. And so if we increase the density of the air coming on the intake, that will dramatically increase the mass air flow rate. Now let's compare that we're running this turbine down at Palm Springs and it's 120, 125. Because of that increased air temperature, that air being drawn in will be at a lot less volume, or density, it will be less dense coming in. So that will affect and drop down the mass flow air rate. The other thing about this is within the combustion can, the primary air is used for mixing that fuel-air ratio, but a portion of the primary air, and again even some secondary air, is used to cool the metallic components of that combustion can. So the can is made out of steel, and you have to be within the limitations of that material, and you use air to cool that. So as you decrease the air intake, not only will you be able to you will not be able to burn quite as much fuel, but you will also have to decrease the fuel rate to keep the temperatures in line, because the temperatures with a decreased mass flow rate will tend to increase. Now, when we look at this even too as a convergent-divergent process, the air is coming into the inlet of the compressor, and these would be, this first stage would be the inlet vanes, and they are directing the air coming in against the compressor vane, and that compressor vane is spinning, and it is attached to the drive rotor, and it is going to impart a velocity to that incoming air. It's going to increase its velocity. The one thing to talk about these rotor blades or vanes is the rotor blades themselves are a airfoil shape. So similar to what we were talking about on the steam turbines, these have a definite airfoil shape, and they have a corresponding optimal angle of attack with the air striking the front of those blades. But anyway, from the inlet vanes, then you have your compressor rotor blades, and then progressively you have a stator vane. The stator vane themselves are convergent divergent. They have at the beginning, they converge down, cause the air to converge a slight amount, and then expand a slight amount. And that velocity of the air that it was imparted on the rotor blade is now transformed into pressure. They also have a very important function, is that they change the direction of flow when to aim the air coming out of the stator vane against the next stage rotor blade at the proper angles. In other words, to control the angle of attack. And usually over each stage you have a 1.2 pressure increase. Now that high pressure air goes into the combustion chamber, where you have this divergent process again. It's opening it up into a larger chamber, and that has a corresponding decrease initially in pressure. But then again, we're burning fuel, and we're going to increase the volume as it goes down this process. On actual compressors, they have about a 50% reduction staging. Compressor stall is when you have a reduction in the mass flow rate going through the compressor. And anything that will disturb that flow being constant can induce compressor stall. The compressor is supplying air into the combustion section. So if for any reason that the mass flow rate suddenly decrease going into the combustor, that will affect the temperatures in the combustor dramatically. Again, one of the things that the air does is not just mix and burn with the fuel, but it serves to cool the components of the combustor. So if there is a sudden decrease in the output of that compressor, it will tend to produce much higher gases, temperature gases in the combustion, which will overheat this engine very quickly. Now, what causes the compressor rotor to decrease its output? And it's typically derived from the fact that the turbine rotor blades the compressor rotor blades can stall, and it is derived around the angle of attack of the air that's hitting the leading edge of those blades. So again, with this subject of stall, what is one of the things that can cause this is variable speed operation. So let's say you have a gas turbine being used to drive a electrical generator, and that generator is always at 900 RPM. The rotor will always spin at a constant RPM. This somewhat reduces or considerably reduces the problem with compressor stall. Then the only time that they're worried about compressor stall is when you start the unit up, because you're going to have to spin this unit up and ignite the fuel, and as it's coming up to speed, you might be able to run into conditions of stall. But once it's at a continuous operation, stall is generally not much of a problem. But let's take the LM2500 that we're running this for ship's propulsion, and that turbine is going to increase and decrease in speed considerably. And under those conditions, with all this variability, then you will have or can sustain problems with compressor stall. And again, when we're talking compressor stall, primarily it is to do with the velocity of the air going through the engine, and because of the changes in velocity of the turbine blades themselves, the angle of attack that air is hitting the leading edge of that compressor blade. So if we can adjust for angle of attack, we can minimize or significantly reduce these effects of stall. So one of the things is to prevent stall is to avoid low power operation. They have an idle speed that's pretty high, and that will help going down into these levels where your compressor will have a low output and could potentially stall, and also has the compressor is giving enough flow rate through the combustion chamber to not only burn the fuel but cool the components. Bleed. A portion of the compressor air from this actual compressor is taken off to do other things, mainly to do cooling of components within the turbine. Well, if we bleed off some of that air, that changes that mass flow rate and the velocity of that air going through the compressor section, which can change the angle of attack. Think of this as a plane at high speed, or if you're slowing down to land a plane. What you'll see when planes slow down to land, they'll increase the angle of attack. They'll rotate the nose up a little bit to give the proper angle of attack at that lower velocity of the plane moving through the air. This is similar. There's also inlet guide vanes that are variable. Now, the inlet guide vanes is the first set of blades that you see. If you look down the bell mouth, if you look into the throat of this turbine, the first set of blades that you see are the inlet guide vanes, and they are directing the air at the proper angle against the first set of compressor blades. Then behind that, you're going to have this blade vane as you work down. You can have variable stator vanes. Now, each one of these stator vanes can be manufactured so that you have an adjustment, and you have an adjustment arm, and we'll go into that and show you how this is done. But I can rotate each one of those vanes around the whole circumference of this engine in that compressor section. And what that will do is direct the air against the corresponding next blade at an angle that is appropriate. So we can change or rotate the blades so that the airflow is appropriate, and that can for that mass flow rate and different conditions, and then that will help to eliminate stall. The next one we'll talk about very briefly, because we're going to look at that as we go down, is a twin spool compressor. We've been talking primarily here about a set of turbine blades that are deriving the power to drive the compressor as a whole. There are situations, and again, this is with some engines to help with this idea of compressor stall, where they separate the compressor into two stages, a low pressure stage and a high pressure stage. And each one of these two stages has a separate turbine wheel that will drive that section of the compressor. And they can run at different speeds separate from each other, and they will find their own equilibrium under different loads and different conditions. And this helps with eliminating some of the problems with the compressor stall. So again, one of the ways is, and this is what they're showing with this bleed valve, is some of that air that is produced from that compressor can be bled off, which will change the mass flow rate going through and somewhat change the velocity of that going through, and that has an effect on the angle of attack. So this is one of the things that is done to help prevent stall. The inlet guide vanes, this ring right in the front, and it's in two halves, an upper and a lower section. And there is, if you look carefully, there is an arm, a control arm here, that when activated, and all of these would turn at the same time, would rotate these blades, and then the air passing through that blade, as I'm rotating it, that will change the angle that it exits the inlet guide vane. And then that is going to strike your compressor blades. So we can adjust the inlet guide vanes so that they always have the right angle of attack striking the next compressor blade. Well, after this, and that's within this casing, there is your stator vanes. Okay? And each one of those may have an adjustment so that you can also change the angle of attack. So on the twin spool, we're not going to talk about in the back here, this is the power turbine. We're only going to talk about the jet engine itself for this small portion of this. And this has a low pressure compression stage and a high pressure compression stage. Now, it's the same kind of the thing that we were looking at the one previous. It's just we've separated this so into two sections. And then we have two drive shafts through the center here. This one attaches to these two turbine blades, which are developing power to drive this low pressure section. And then we have another wheel here through this drive shaft, which is tubular. So I have one drive shaft going down the middle of another one, driving the high pressure part of the compressor. The advantage to this is, again, each section can find its own equilibrium under different conditions, and this helps or not eliminate, but this helps reduce the problems with compressor stall. So this idea again of, and we're going to this B. So A was compressor. B now is going into the combustor. And this section now is divergent. And then you can see that as we go in, it is expanding into this area. And you have a diffuser here. A diffuser is somewhat like very close to being the same as we were talking about a compressor vane. And it is, but it also helps to direct the airflow. And as the air and fuel are burned in this area, you're going to get a corresponding temperature increase and a velocity increase as far as it exits. Okay, C, again, convergent. So we expanded into this combustor. We burned the fuel, which dramatically increases temperature and volume, because the volume of the combustion gases, they get hotter. That volume is, the gases need more volume. And we're going to go through a nozzle, and then we're going to strike the turbine rotor. And after the turbine rotor, it's going to exhaust. So within this turbine reaction staging, this high velocity, high temperature gases cause the rotor to turn while expanding even more into a larger volume. So reaction staging is primarily used with gas turbines because it is the most efficient over a very wide range of operating conditions. Typically, steam turbines are comparatively have a much narrower range of operating conditions. Gas turbines run over a very, very large RPM range. In fact, some of them can run up as much as 45,000 RPM. And so typically, gas turbines use reaction blading. So this is just, the chart is comparing them. Again, and when we look at stage efficiency, this is the Curtis stage, which we were talking about on a steam turbine. We use in the beginning, and then this is a standard impulse Rateau stage, and this is the reaction. But over a very large range of velocities, it is the most efficient. So we're going to stop here. Look forward towards the next part 2. Thank you very much.